Yes, students, welcome back to my class number 6 on P block elements. So in the previous video we were talking about the trihalides of boron and trihalides of aluminium. We understood a wonderful concepts like back bonding and dimerization. So now we will quickly look into the structure of aluminium chloride and then we will solve the MCQs from MTG fingertips. Okay, yes, look at the structure of aluminium trichloride because it is there in your NCERT textbook and it is also very important for NEET examination. Okay, I told you that aluminium trichloride will exist as dimer. It will undergo dimerization. Okay, aluminium chloride, in aluminium chloride, aluminium will satisfy its electron deficiency through what? Dimerization. So it will undergo dimerization and it exists as what? Al2Cl6, correct? Look at the structure of aluminium here. Aluminium, two aluminium atoms. Okay, yes, aluminium trichloride, isn't it? AlCl3. AlCl3. Okay, yes. See the structure of aluminium trichloride. Now, okay, what is going to happen? The lone pair of electrons, chlorine will transfer its lone pair of electrons to the vacant orbital of aluminium. Is it correct? Okay, yes. Here also, okay, chlorine will transfer its lone pair of electrons to the vacant orbital of, okay, this aluminium and it forms a coordinate bond. See, these two chlorine atoms are called as bridged chlorine. Okay, these and this chlorine, they are called as what? Bridged chlorine, whereas these four chlorine atoms are called as terminal chlorines. Okay, terminal chlorine. Are you getting my point? Okay, so understand this structure of aluminium. See this, see the two aluminium atoms and four chlorine, these four chlorine, they all will lie in one plane. Okay, they all will lie in one plane. Okay, so all of them will lie in one plane. The two aluminium atoms and the four chlorine atoms, the two aluminium atoms and the four chlorine atoms will lie in one plane, okay, whereas the bridged chlorine atoms, one bridged chlorine atom will be above the plane and the other bridged chlorine atom will be below the plane. Understood? Okay, one bridged chlorine will be above the plane and another bridged chlorine will be below the plane, whereas the two aluminium atoms and the four chlorine atoms will be in one plane. It will be in one plane. Understood? Okay, so what are these four chlorine atoms called as? This and this, they are called as terminal chlorines. Terminal chlorine, whereas these two chlorine atoms which are out of the plane, isn't it? This chlorine is above the plane and this chlorine will be below the plane. They are called as bridged chlorine. Understood? See this, let us call this bond and this bond. See this, all these four bonds, okay, they will be of equal length. That is, it will be of 206 picometer. Okay, are you getting my point? See this bond, yes, this, okay, this bond, all of them are equal, okay, and they are equal to what? 206 picometer, whereas this bridged bond, this bond, okay, this will be longer than this bond. This AlCl bond will be longer than this AlCl bond and it will be of, okay, 221 picometer. 221 picometer. Are you getting my point? So this bridged AlCl bond will be more than the terminal AlCl bond. Okay, so this is 221 picometer, whereas this is 206 picometer. Here the bond angle is going to be 10 degree. This bond angle is going to be 78 degree, and this bond angle is going to be 80 degree. Okay, 80 degree. Are we clear? Okay, so understood. So two aluminium atoms, four chlorine atoms in one plane. This bridged chlorine will be above the plane and this bridged chlorine will be below the plane. This bond length will be shorter than this bond length. Okay, so here we have three different bond lengths. This bond length is 110 degree, this bond length is 78 degree, and this bond length is 80 degree. Okay, see, we call this bond now, we call this structure as, okay, three center. Very important. This structure is called as, okay, three center 4 electron system. We call the structure as 3 center 4 electron system. Why? Look at this. If I consider this bond, okay, yes, how many atoms are there? 1 2 3 center. Okay, how many electrons in this bond? 2 electrons. How many electrons in this bond? 2 electrons. 2 electrons plus 2 electrons, 4 electrons. That is why it is called as 3 center, okay, 4 electron bonds. So understood? Okay, 3 center 4 electron system. This structure is called as what? 3 center 4 electron system, and we call this bond, we call this AlCl, okay, Al. We call this bond as, okay, banana bond. Okay, what is this bond called as? This bond is called as banana bond. Understood my point? Okay, are we clear? So what is this system known as? What is this structure called as? 3 center 4 electron. 3 center because there are 3 shared atoms, isn't it? AlCl, Al, and 4 electrons. Between these two electrons, between these two electrons, therefore it is 3 center 2 electron. And what do you call this bond as? A special type of bond. This bond is called as what? Banana bond. Understood? Okay, yes. Students, now we will solve some typical problems for NEET from your MTG fingertips. So here is my question. Okay, the reason behind the lower atomic radius of gallium as compared to aluminium, we understood this in the very first video lecture on P block. Is it correct? Okay, so we have boron, aluminium, gallium, indium and thallium. Okay, so as we go down the group, atomic radius should increase. Okay, as we go down the group, okay, as we go down the group, okay, atomic radius should increase, isn't it? So now we have boron, aluminium, gallium, indium and thallium, isn't it? So as we go down the group, atomic radius should increase. Okay, correct? But we know that atomic radius increases from boron to aluminium, but from aluminium to gallium it decreases. Why it decreases from aluminium to gallium? Because I have explained. Okay, in gallium, okay, so what is it? Okay, in gallium there will be, okay, there will be inner d orbitals, completely filled d orbitals. Inner d orbitals will exhibit pore shielding effect. Because of pore shielding effect, the last electrons, okay, will be pulled towards the nucleus. When the last electrons are pulled towards the nucleus, okay, the atomic radius will decrease, isn't it? Okay, you can check. So boron, atomic number 5, 5 plus 8, 13, 13 plus 18, 13 plus 18 is how much? Okay, yes, 31, isn't it? Okay, the atomic number of gallium is 31. What is its electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p, okay, 6. And then what? 4s2, okay, 4s2. Okay, so 5 plus 8 is 13. 13 plus 18 is how much? 13 plus 18 is 31. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, okay, yeah, 3s2, okay, 3p6 and then 4s2, okay, 3d10, correct? Okay, 4p1, understand this, okay, observe this. So there are inner completely filled d orbitals. Due to inner completely filled d orbitals will exhibit pore shielding effect. Because of pore shielding effect, okay, the outer electrons will be pulled towards the nucleus. When the outer electrons are pulled towards the nucleus, the atomic radius will decrease. That is why the atomic radius of gallium is less than that of what? Aluminium. So what is the answer? Okay, yes, it is because of pore screening effect of d electrons for the outer electrons, okay, from increased nuclear charge, isn't it? So the correct answer is going to be, okay, answer A, isn't it? Yes. Okay, yeah, next question. The first ionization enthalpy of aluminium is lower than that of magnesium. Why? Okay, very logical question. Okay, why the first ionization enthalpy of aluminium is lower than that of magnesium? Aluminium, what is the atomic number? 13. What is its electronic configuration? 1s2, 2s2, 2p6, correct? Okay, 1s2, 2s2, 2p6, and then 3s2, okay, yeah, 3p1, correct? Okay, 1s2, 2s2, 2p6, 3s2, 3p1, isn't it? Okay, now magnesium, atomic number 12, what's its electronic configuration? 1s2, 2s2, 2p6, 3s2, isn't it? Now, okay, the question says the first ionization enthalpy of aluminium is lower than that of magnesium. Okay, so first ionization enthalpy is obtained. First ionization enthalpy is obtained when I remove the first last electron. Okay, so from aluminium I have to remove the last electron. Which is that last electron? 3p. I have to remove the last electron from 3p orbital, whereas in magnesium, okay, the last electron has to be removed from s orbital. Okay, look at here, in aluminium the last electron has to be removed from 3p orbital, whereas in magnesium the last electron has to be removed from s orbital. Okay, 3p orbital, 3s orbital, 3p orbital, 3s orbital. We know 3s orbital will be near to the nucleus. Since the 3s orbital is near to the nucleus, okay, effective nuclear charge will be more, hence the 3s electron will be tightly held to the nucleus, isn't it? Since the 3s electron is tightly held to the nucleus, okay, the removal of the last electron becomes difficult, correct? Whereas in aluminium the last electron is in 3p orbital, which is away from the nucleus. Since the last electron is away from the nucleus, effective nuclear charge will be less. Since the effective nuclear charge is less, the last electron can be easily removed from the orbital, correct? Isn't it? So that is why it is easy to remove this electron than this electron. Why it is difficult to remove this electron? Because this electron is in s orbital. S orbital will be near to the nucleus. Since the s electron is nearer to the nucleus, the removal of electron becomes difficult. So what is the correct answer? The size of aluminium is bigger than magnesium. Ionization enthalpy decreases in period. No. What is the answer? It is easier to remove the electron from, okay, unpaired 3p than paired 3s. Yes or no? Yes. This is correct. Okay. So the answer is going to be, it is option C. Understood? Correct. Yes. Next one. Okay, group 13 elements show, I told you, yeah, what is the general outer electronic configuration of group 13 elements? It is ns2 np1, isn't it? The general outer electronic configuration of 13 group elements is ns2 np1, correct? Okay, so they can lose the outermost p electron to and it exhibits +1 oxidation state, or else they can remove, okay, they can lose all the 3 electrons and they can exhibit +3 oxidation state. Therefore 13 group elements will exhibit +3 oxidation state and +1 oxidation state. I have also told you that boron, aluminium, gallium, indium are stable in +3 oxidation state, whereas thallium is stable in +1 oxidation state because of which effect? Inert pair effect. Understood? Okay. So what are the common oxidation state of 13 group elements? It is +3 and +1. Therefore the correct answer is, yeah, okay, it is option C, +1 oxidation state and +3 oxidation state. Option C is the correct answer. Yes. Next question. Okay, aluminium exhibits +3 oxidation state. As we move down the group, the +1 oxidation state gets more stable. Yeah, I told you here. Okay, boron, aluminium, gallium, indium, they exhibit which oxidation state? +3 oxidation state, whereas thallium will exhibit +1 oxidation state. Why thallium will exhibit +1 oxidation state? Okay, yes, and thallium is more stable in +1 oxidation state because of a phenomena called as inert pair effect. Okay, isn't it? So what is the reason? This is a consequence of what? Inert pair effect. Therefore the answer is, it is option B. Any doubts? Okay, yeah, next question. Yes, okay, yeah, group 13 elements show +3, +1 and +3 oxidation states. Group 13 elements show +1 and +3 oxidation state. Relative stability of +3 oxidation state may be given as Okay, yes, again the same thing. So plus 3 oxidation state and plus 1 oxidation state. So as we move down the group, inert pair effect increases. When inert pair effect increases, the stability of plus 3 oxidation state decreases and stability of plus 1 oxidation state increases. So what is the order of stability of plus 3 oxidation state? Yeah, boron is more stable in plus 3 oxidation state than aluminium, okay, than gallium, okay, than indium, than thallium. Okay, thallium is least stable in plus 3 oxidation state. Why thallium is least stable in plus 3 oxidation state? It is because of inert pair effect. Thallium is more stable in plus 1 oxidation state rather than in plus 3 oxidation state. So what is the order of stability of plus 3 oxidation state? Yeah, boron is more stable than aluminium ion, aluminium is more stable than gallium, than indium, than thallium. So what's the correct answer? It is option B. Correct. Yes. Next question. Okay. Which of the following metals do not show inert pair effect? Okay. Yes. Inert pair effect is observed. Inert pair effect is observed if there is completely filled d orbitals and f orbital. Okay. If there is completely filled d orbital and f orbital, they show inert pair effect. Okay. But look at aluminium. What is the atomic number of aluminium? It is 13. What is its electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p1, isn't it? Is there any inner completely filled d orbital? No. Is there any inner completely filled f orbital? No. That means there is no inner d orbital, no inner f orbital. Okay, correct? So that means there will be no inert pair effect. Therefore, I can say aluminium does not show inert pair effect, whereas thallium, indium, gallium, they contain inner completely filled d orbital and f orbital. Hence, they will exhibit inert pair effect, whereas aluminium does not exhibit inert pair effect. So what is the correct answer? It is option D. Yes. So next question. Okay. So in BX3, the BX distance is shorter than what is expected theoretically, because in BX3, BX distance is shorter than what is expected theoretically, because, yeah, very simple. I have told you, I have discussed about back bonding, isn't it? Okay, look here. See, in boron trifluoride, observe this. Okay, boron is sp2 hybridized and it is trigonal planar shape. Trigonal planar shape, isn't it? It is trigonal planar shape. Correct? Okay. Boron will have what? Vacant 2p orbital. Fluorine has lone pair of electrons in 2p orbital. Now, okay, fluorine has lone pair of electrons in 2p orbital. We know fluorine will donate its lone pair of electrons from its 2p orbital to the vacant 2p orbital of boron. Okay, as a result, there is a coordinate bond formation. Whenever there is a coordinate bond formation, okay, there will be partial double bond between what? Boron and fluorine. There is partial double bond between boron and fluorine. Okay, yes, now we know double bond, okay, triple bond and single bond. Triple bond is smaller than double bond, double bond is smaller than single bond. Correct? Okay, this bond length is more, this bond length is less, this bond length is still less. So because of back bonding between boron and fluorine, there is partial double bond character. Because of partial double bond character, this bond length will be less when compared to this and this. This is purely single bond, this is purely single bond, whereas this is partial double bond. Hence, the bond length will be less than this and this. Is this correct? That is what it is telling. Yeah, okay. In BX3, BX distance is shorter than expected. Why BX distance is shorter than expected? Because of partial double bond character. Why there is partial double bond character? Because of back bonding. So what is the correct answer? Yes, BX has a double bond character due to back bonding. Hence the correct option is option B. Okay, yeah, next question. Yeah, okay. Yes, why do boron and aluminium halides behave as Lewis acids? Very simple question which has been already explained in my video lecture 4 and video lecture 5. Okay, why boron? Why do boron and aluminium halides behave as Lewis acids? Okay, Lewis acids means, what are Lewis acids? They are electron acceptors. Okay, why do they accept electrons? Because they are electron deficient. Okay, they are electron deficient, isn't it? Okay, since they are electron deficient, they accept electron pairs. That is why they are called as Lewis acids. Now consider boron halides and aluminium halides. Okay, how is boron trihalide? Observe here, boron trihalide and aluminium trihalide. Okay, count the number of electrons around boron and aluminium. Okay, one bond refers to 2 electrons, isn't it? Okay, yes. So there are 2 electrons here, there are 2 electrons here, and there are 2 electrons here. So the central atom is surrounded only by 6 electrons. 2, 4, 6. The central atom is surrounded only by 6 electrons. It is deficient of 2 electrons to complete its octet. Since it is electron deficient, it can accept electrons. That is why it is a Lewis acid. Even in case of aluminium, count the number of electrons, 2, okay, 4 and 6. Okay, so aluminium is surrounded by only 6 electrons. It is also deficient of 2 electrons to complete its octet. Hence, even aluminium is electron deficient. That is why it acts as Lewis acid. So what is the correct answer? Both the halides, okay, can accept electrons from a donor to complete their octet. Yeah, okay, they can accept electrons. Why they can accept electrons? Because they are deficient of how many electrons? 2 electrons to complete their octet. So what's the correct answer? It is option A. Correct? Yeah. Next question. Okay, which of the following, okay, hydroxides is acidic? Okay, which of the following hydroxide is acidic? Okay, observe this. If I consider oxides and hydroxides of boron family, we have different oxides like B2O3, okay, Al2O3, okay, Ga2O3, In2O3 and Tl2O. Please remember, thallium will form different oxides and different hydroxide. Okay, so and also hydroxide, BOH thrice, okay, ALOH thrice, isn't it? Okay, GaOH thrice, yes, InOH thrice, but this is going to form TlOH. That's it. See, the oxides and hydroxide of boron, they are purely acidic in nature. They are purely acidic in nature because boron is non-metal. Okay, the oxide and the hydroxide of non-metals will be what? Acidic in nature. Okay, whereas aluminium oxide and aluminium hydroxide is amphoteric, because aluminium is an amphoteric metal. They're amphoteric. They can behave both as an acid as well as what? Base. Whereas the oxides and hydroxides of the rest of the elements are purely basic, because all these are pure metals. Gallium, indium, thallium, gallium, indium, thallium, they are pure metals. The oxides and hydroxides of metals are basic. Okay, so these oxides and hydroxides are basic, whereas the oxide and hydroxide of aluminium is amphoteric. The oxides and hydroxide of barium is acidic. Therefore, the correct answer is, which of the following hydroxide is acidic? The correct answer is boron hydroxide. Boron hydroxide. Understood? Yeah. Next question. What is the decreasing order of power of boron halides? Okay, to act as Lewis acids. Yeah, I have discussed already. Clearly in my video lecture 5. What is the decreasing order of power of boron halides to act as Lewis acids? So we have boron trifluoride, boron trichloride, boron tribromide, and boron triiodide, isn't it? Okay, all of them are Lewis acids. No doubt. Why they are Lewis acids? because the central atom boron is deficient of 2 electrons. It is ready to accept electrons. That is why they are Lewis acids. But which among them is a strong Lewis acid? I have told you that boron triiodide is a strong Lewis acid than boron tribromide, then boron trichloride, then boron trifluoride. Why boron trifluoride is a weak Lewis acid? Because of what? Back bonding. Okay. So due to back bonding, fluorine will transfer its lone pair of electrons to boron. When fluorine transfer its lone pair of electrons to boron, okay, the electron deficiency of boron will be reduced. Hence, okay, it will no more be electron deficient, and hence it will no more act as a Lewis acid. Whereas in boron tribromide and boron triiodide, there is no back bonding. There is no back bonding. Okay, why there is no back bonding? Because here the energy difference is large. The energy difference will be large between the orbitals of boron and the orbitals of bromine, orbitals of boron and orbitals of iodine. Okay, since the energy difference is large, they cannot form back bonding. When they cannot form back bonding, boron remains as electron deficient. It will accept electrons, and hence it is going to be a strong acid. Okay, so what is the order of Lewis acids here? Yeah, boron. Okay, we have only 3. We know boron tribromide is a strong Lewis acid than boron trichloride, which is a strong Lewis acid than boron trifluoride. Understood? So guys, okay, yeah, next question. Okay, yes, the next question says, okay, conceptual question, but a simple question. Observe this. Okay, a metal X reacts with aqueous sodium hydroxide solution, okay, to form Y and an highly inflammable gas. A metal X reacts with aqueous NaOH solution to form Y and an highly inflammable gas. Solution Y is heated. Okay, now solution Y is heated. Carbon dioxide is poured through it. Z precipitates out, and Na2CO3 is formed. Z on heating gives Al2O3. Identify X, Y, and Z. Okay, bit a long question here. So now observe this. A metal X is reacting with aqueous NaOH. See, when we discussed, okay, the characteristic features of boron family, so I have told you boron, aluminium, gallium, indium, and thallium. See, since these are metals, they react only with acids. These 3 are metals, therefore they react only with acids. Whereas aluminium is an amphoteric metal. It reacts both with acid as well as base. Whereas a boron, it will not react with acid or base as such, but acids, okay, will oxidize boron. Acids will oxidize what? Boron, but not base. Now the question is talking about sodium hydroxide. If the question is talking about sodium hydroxide, it's a base. That means the reaction is carried out with a base. If the reaction is carrying out with a base, then the metal should be what? Aluminium, isn't it? The metal should be aluminium. So we have 2 options, option A and option D. Okay, so therefore X should be aluminium. Yeah, okay, X should be aluminium. So let us write the reaction. Aluminium reacts with sodium hydroxide, I told you, okay, to form a peculiar compound. What is that? NaAlO2 with the liberation of which gas? Hydrogen gas. Observe, understand the question. A metal X, okay, reacts with sodium hydroxide to form Y. So this is Y, okay, and an highly inflammable gas. We know hydrogen gas is an highly combustible gas. It's an highly inflammable gas. So what is X? Aluminium. What is Y? Sodium aluminate. Now, okay, Y, that is sodium aluminate, okay, yes, is heated and carbon dioxide is poured. Okay, it is heated and carbon dioxide is poured. So when sodium aluminate is heated and carbon dioxide is poured, it is going to form AlOH thrice, and it gives sodium carbonate, Na2CO3. Observe, okay. So when solution Y, this is Y, isn't it? solution Y is heated and carbon dioxide is poured through it, Z is precipitated out. So which is Z? Z is precipitated out, okay, and sodium carbonate is formed, isn't it? Therefore Z is AlOH thrice. Now, okay, AlOH thrice, AlOH thrice, upon heating it gives what? Al2O3 plus H2O. Observe the next statement. Z, this is Z, isn't it? Z on heating gives Al2O3. So you have to identify X, Y and Z. What is X? Aluminium. What is Y? NaAlO2. And what is Z? AlOH thrice. Therefore what is the correct answer? Yes, option A is the correct answer. So X is aluminium, Y is sodium aluminate and Z is aluminium hydroxide. Okay, yeah, next question. Okay, what is the next question? Yeah, boron is unable to form, okay, boron hexafluorate. Why? Boron is unable to form boron hexafluorate. Why? Okay, observe, what is the electronic configuration of boron? Okay, atomic number of boron is 5. What is its electronic configuration? 1s2, 2s2, 2p1. Is there any d orbitals in boron? No, there are no d orbitals in boron. Okay, therefore what is the covalency of boron? Covalency of boron is, okay, covalency of boron is 4, because there are only 4 vacant, there are only 4 outermost orbitals. Therefore the covalency of boron is 4. Okay, now in boron hexafluoride BF6 3 minus, the covalency of boron, okay, seems to be 6. Can the covalency of boron be equal to 6? No, the covalency of boron cannot be equal to 6. The covalency of boron can only be equal to 4. Why the covalency of boron can only be equal to 4? Because there are no d orbitals. Since there are no d orbitals in boron, covalency of boron is restricted to 4. Hence it cannot form BF6 3 minus. Okay, observe this. So boron is unable to form BF6 3 minus ions due to the non-availability of d orbitals. Since there are no d orbitals in boron, the covalency of boron is restricted to what? 4 on 4. Hence it can only form BF4 minus. It cannot form BF6 3 minus. So what is the correct answer? It is non-availability of d orbitals. Okay, so the last question. Okay, which of the following is a correct representation of the reaction when boron trifluoride reacts with ammonia? Yeah, now he is talking about the reaction between boron trifluoride and ammonia. We know boron trifluoride BF3. We know boron trifluoride is electron deficient, isn't it? Electron deficient. So it acts as what? Lewis acid. It acts as Lewis acid. Now this boron trifluoride is reacting with ammonia. In ammonia, nitrogen has lone pair of electrons. Okay, so we know ammonia is Lewis base. Okay, yes, it is electron donor. It is electron donor, whereas this is electron acceptor. Okay, so nitrogen will donate its lone pair of electrons to boron. When nitrogen donates its lone pair of electrons to boron, there is a coordinate bond formation. Observe this. There is a coordinate bond formation between ammonia and boron trifluoride. Okay, got it? So this is the compound form. So what is the correct reaction? The correct reaction is, yeah, this one. Nitrogen will donate its lone pair of electrons to boron because boron is electron deficient, ammonia is electron rich. Lewis acid, Lewis base will combine to form an adduct. What is this called as? This is called as adduct. So what is the correct answer? Okay, the correct answer is 1 is incorrect, 2 is correct. No, 1 is correct, 2 is incorrect. Therefore the correct answer is option B. Understood? So guys, so that's all for this video. We will continue with some of the important compounds of boron and we will continue with group 14 elements in the next video. Okay, thank you.